This position paper is a pilot program research plan to understand and anticipate cascade triggers in the critical infrastructure. It is an articulation of a problem associated with a software property that is not yet well understood. A cascade trigger is a software property associated with system of systems whose presence must be anticipated and whose level of governance control must be understood and calibrated in terms of probability of occurrence and certainty of effective mitigation. A vulnerability in the critical infrastructure system of systems, a cascade trigger may originate in one industry sector only to see its effects present themselves as disruptions in one or more industry sectors. Understanding and identifying cascade triggers and how to mitigate them will provide important insights necessary in both mitigating the effects that may occur inadvertently and defending against cyber attacks that would purposely exploit them. Anticipating and avoiding cascade triggers is an essential step in the integration engineering of the critical infrastructure systems of systems. Specifically, the harmonization of context and culture in domain engineering associated with industry sector diversity in architecture, models, and patterns, including their representation. While proof of existence of cascade triggers has been documented and measured, and their calamitous effects have been chronicled in popular books sounding the alarm for the general public in the electrical, banking and finance, and internet industry sectors, the sense of urgency to innovate and originate repeatable practices for their systematic identification and mitigation has yet to be felt in the government research and development community. Cybersecurity is a threat to global competitiveness and national security. On global competitiveness, company value propositions span trust, loyalty, satisfaction, reputation, economics, and high assurance. Just what are the ways cybersecurity impacts each of these business goals? On national security, the military is charged with defending the country on land, sea, air, and space. Just what are the ways cybersecurity impacts each of these theaters of operation? Global competitiveness and the mission of the military-industrial complex are linked by the industry sectors that make up the critical infrastructure, such as electrical, water, oil and gas, telecom, GPS, banking and finance, transportation, and medical and emergency services. Just what are the ways cybersecurity impacts each of these industry sectors? Can a cybersecurity perfect storm be triggered by a single fast-moving attack or natural event? Or does it take a carefully coordinated attack scenario? In any event, what tactics offer the best protection? More specifically, what is the least set of supervisory control operations best able to sustain a system of harmoniously cooperating distributed processes? To what extent is this set of operations currently embedded in the nation's critical infrastructure? What improvements are indicated to elevate that protection to a minimally acceptable state? The pilot program would serve as a visible demonstration of software innovation and would provide a roadmap and tool for renovating the risk management paradigm employed for similar complex problems. The initial steps would be aimed at bounding the problem for research while preserving and building in the scalability of the research models envisioned. The goal: obtain intellectual control of targeted properties of the nation's critical infrastructure through supervisory control policies and protocols. The objectives: model the supervisory control policies and protocols of selected sectors within the critical infrastructure along with their interactions and the behavior of targeted properties. Determine the predictive impacts related to the behavior of targeted properties while operating under various levels of stress. Assess the effectiveness of selective prescriptive measures introduced through changes in supervisory control policies and protocols in alleviating levels of stress. In my comment to the Cyber Commission on April 14, 2016, at its kickoff meeting at the Department of Commerce, I urged the call to action on Cascade triggers when I stated the most consequential threat to resilience lies in the cascading and propagating triggers that lie hidden in the complexity of critical sector interactions and dependencies inherent in the system of systems that make up the critical infrastructure. Without anticipation and avoidance, cascade triggers are left unattended. Following up on this call to action with this position paper, I propose the following pilot program steps for a research plan to better understand the systematic anticipation, investigation, detection, mitigation, and avoidance of cascade triggers in the critical infrastructure system of systems. Here, evidence of industry sector understanding is presented in artifacts with multidimensional viewpoints as suggested below. Conduct Team Innovation Management Lab with industry sector experts. Produce top-level operational concept industry sector diagrams. Create one-page text industry sector descriptions. Create entry task validation exit industry sector diagrams. Determine recovery time objectives for industry sectors. Produce multiple clusters of 3 industry sectors and a composite cluster. Identify industry sector cascade triggers and mitigation consequences. It would appear that the NIST Cybersecurity Center of Excellence is a natural point of responsibility and partnership to facilitate an immediate go-ahead for this critical initiative. The critical infrastructure is composed of the numerous industry sectors that do the heavy lifting. Some key sectors are listed here. Utilities and energy contain power generation and distribution systems, nuclear power control systems, and energy resource allocation systems. Telecommunications contain network control and switching systems, satellite control and management systems, and mobile communications systems and protocols. Banking and finance contains electronic commerce and electronic funds transfer systems, transaction processing systems, security and privacy management systems, and network management systems. Transportation contains route management and collision avoidance systems, avionics systems, air traffic control systems, navigation and position location systems, and embedded automobile control systems. Medical systems contain medical device control systems, patient record systems, and insurance and payment systems. Global Positioning System is composed of a constellation of orbiting satellites and a ground station performing functions such as network control, ephemeris and clock, mission scheduling, space vehicle positioning, and space vehicle command and status, and delivering positioning data to user receivers on land, air, and sea. Water is composed of wastewater sewage collection, filtration, and distribution. Understanding the interactions between industry sectors needs to be done in a systematic, repeatable manner by asking industry sector experts themselves. This can be approached using the Team Innovation Management and its lab. Select critical infrastructure industry sectors to pilot and identify named representatives for each industry sector. Obtain shared vision on the value proposition and integration engineering approach, and produce an operational concept of industry sector interactions and state transitions. Model the system of systems architecture selected, demonstrate the model, and exercise it with an eye on industry sector interfaces, state transitions, and cascade trigger identification and mitigation. In the Team Innovation Management Lab, participants are paired up for their appearance in the intersection of innovation, where the application of domain and information technology clash, and where each pair generates as many good ideas as possible. Innovation lies at the intersection of invention and insight, dependent on ideas, collaboration, and expertise. At the intersection, there are many ideas and many combinations, and there are many forces, including culture, science, and the leap of computation. The intersection is modeled as shown in the figure. Once at the intersection, it is the role of the industry sector personnel to generate as many ideas as possible. Some will simply be directional, rules-based workforce reducing efficiencies. Directional ideas spawn new features and capabilities, are often customer-driven, and can be implemented by planned and predictable steps. These new features extend the dwell time of the product line within the niche. Others will be intersectional, process pattern transformations that involve radically new directions, driven by the cross-discipline clash with new directions not based on detailed knowledge, and ideas originated from people least expected. These new directions may open new niches. Industry clusters are formed by selecting interacting industry sectors in groups of 3 for close analysis and inspection of interfaces, data exchanges, coordinated recovery time objectives, and cascade triggers. Using the TIM Lab construct, conduct a systematic industry sector crawl at the intersection of innovation. Here, representatives from each of 3 industry sectors, A, B, and C, line up for the TIM Lab. First, members of the industry sector A enter from the left, industry sector B from the top. A member of industry sector A and a member of industry sector B enter the intersection and begin a question and answer dialogue. Are industry sectors A and B dependent on each other? How so? Describe the nature of the dependency. Specify the interactions that take place and identify the data input and data output exchanged, along with the frequency of exchange. Record the recovery time objective for both industry sector A and B. Record the possibility of any suspected cascade triggers, their root causes, and the best method for mitigation. Most specifically, record the cascade initiating event and the cascade resulting event, including all industry sectors that may experience the cascade resulting event. What other industry sectors are A and B dependent upon? Continue with subsequent members of industry sector A and B, entering the intersection until each has had a turn to experience the question and answer dialogue. Repeat steps above with industry sector A and C. Again, repeat the steps above with industry sector B and C. Using the information learned at the TIM Lab intersection, each industry sector team is asked to produce a top-level operational concept diagram composed of nodes and annotated arcs, a one-page textual description of industry sector operations, an entry task validation exit industry sector diagram, a recovery time objective for the industry sector, an identification of industry sector clusters, a cluster of 3 industry sectors, and a composite cluster, and a list of suspected cascade triggers for each cluster. The figure illustrates the operational concept as a state machine expressed as nodes and annotated arcs. The text shown is an example of a one-page textual description of the banking and finance sector. The banking and finance sector illustrates the stovepipe cultural environment and technological vulnerabilities that stand ready to trigger societal impact. Its situational dependence on public trust and its operational dependence on electrical and telecom resilience under stress, with its tightly coordinated recovery time objectives, make it vulnerable. In banking and finance, the financial services industry depends on a network of systems that process instruments of monetary value in the form of deposits, loans, funds, transfer, savings, and other financial transactions. The network is composed of banks, other depository institutions, and the Federal Reserve System, as well as underwriters, brokerages, and mutual funds. In addition, there are industry utilities, including the New York Stock Exchange, the Automated Clearinghouse, Depository Trust Clearinghouse Corporation, and the Society for Worldwide Interbank Financial Telecommunications, as well as underlying third-party electronic processing services. The interagency paper pinpoints clearing and settlement systems as the most critical business operations at risk for financial markets and the disruptions of clearing and settlement processes would have on an immediate systemic effect on critical financial markets. The use of the term systemic risk is based on the international definition of systemic risk in payments and settlement systems. The Federal Reserve Board specified that the following functions are critical to the operation and liquidity of banks and stability of financial markets and require same-day recovery. Large value interbank funds transfer, securities transfer, or payment-related services such as Fedwire, clearinghouse, interbank payment system, Depository Trust Clearinghouse Corporation, and the Society for Worldwide Interbank Financial Telecommunications. Automated clearinghouse operators, key clearing and settlement utilities, Treasury automated auction and processing system, large dollar participants of these systems and utilities. The ETX paradigm provides a graphic notation for disciplining the recording of the target process architecture. Entry criteria must be satisfied before beginning the tasks. Task descriptions indicate what is to be accomplished. Validation verifies the quality of the work products and process applied. Exit criteria checklists must be satisfied before completing the tasks. The example shown is drawn from the textual description of the banking and finance sector just discussed. When we look at the nation's critical infrastructure, no industry sector has the defenses to combat the intersection of a neglected software industry with its vulnerabilities and a determined, innovative bad actor intent on launching cybersecurity exploits. The lack of strategic coordination among these industry sectors, and especially the absence of coordinated recovery time objectives, may be setting the table for a coordinated cyber and physical attack. Just what is involved in recovery? The operations involved in recovery state transitions are illustrated in the figure. The steps to reconstitute critical software operations center around the technology for ensuring continuous operations, backing up, switching over, and restarting critical operations. Threats to the survivability of software operations begin with the natural and man-made threats to physical plant, electrical supply, and telecommunications connectivity used by critical software operations. The user of these assets must anticipate and recognize the loss of assets and provide for the reconstitution of the operation. Uh, the owner of the critical software system must resist threats, recognize attacks, and provide for the reconstitution of the operation. Whether the threat is natural or man-made, physical or logical, there is the need to provide for the reconstitution of the operation. A critical software operation whose continuous operation must be assured needs a disaster recovery plan spanning computing equipment, connectivity, software, and operating personnel, along with the transition mechanisms to carry it out. For each critical infrastructure sector, under what circumstances of use are dependent sectors not available? Not available is defined in a specific situation description. For each instance of non-availability, what is the immediacy of need and the required recovery time objective for each? These are expressed in seconds, minutes, hours, days, and weeks. Canonical verification of the statement of critical infrastructure sector dependency is governed by the degree of correspondence where recovery time objectives are established in relationship to immediacy of need. Shortfall reveals technical and management feasibility and state of the practice issues. Operational verification of the statement of critical infrastructure sector dependency is governed by the degree to which the recovery time objective has been coordinated among the prime and support sectors in arriving at a coordinated recovery time objective. Shortfall reveals issues in stovepipe culture, management will, and regulatory environment. A confidence level is assigned to the outcome in terms of high, medium, or low. The next three figures illustrate three increments of industry sector clusters, each composed of three industry sectors, followed by a composite of increments. This one is increment 1, banking and finance. This is increment 2, transportation. Here is increment 3, medical and emergency services. Here is the critical infrastructure composite and their interactions. Each critical infrastructure industry sector is dependent on other industry sectors. The interdependence of electric power, telecommunications, energy, financial, transportation, emergency services, water, food, and so forth is exacerbated by the embedded electronic devices relied on to provide critical controls. Electric power and telecommunications stand out as common critical dependencies for all industry sectors and require special preparation and protection measures. Underneath the surface and hidden in the complexity of critical sector interactions and dependencies are triggers that can result in cascading and propagating effects and impacts. Mostly hidden, cascade triggers may stem from known conditions and system states, including the flash crash, electrical grid physical infrastructure vulnerability, internet distributed denial of service, DDoS, cybercrime, encryption based on deterministic mathematical certainty. The flash crash took advantage of data transmission and trading speed differentials that resulted in wide swings in market prices. Buyers in the futures markets included high-frequency trading firms that buy and sell within minutes. Their tactics of spoofing, layering, and front-running are now banned. Hidden, or in plain sight, cascade triggers are capable of invading various industry sectors in a variety of ways. The transportation sector can be brought to its knees if truck drivers cannot use credit cards to charge for gas tank fill-ups, The medical sector depends on the internet to distribute and present patient electronic medical records on demand just in time. The electrical grid depends on survivable electrical grid with predictable demand profiles matched to planned resources and capacities. The banking and finance sector remains ever conscious of the need to protect next day opening, even in the presence of a flash crash disruption. The users of the telecommunications sector are increasingly vulnerable to internet disruptions like DDoS and encryption-based scams like ransomware. Anticipating, avoiding, and minimizing the effects of these triggers is a responsibility of the resiliency integrator. For example, the banking and finance sector must remain ever vigilant during the trading day for evidence of triggers that might impede next day opening of the market. Here, anticipation and avoidance is preferred over recovery, cleanup, and delayed market opening in maintaining trust in the banking and finance sector. Underlying cascading and propagating triggers hidden in the complexity of critical sector interactions and dependencies must be anticipated, avoided, and minimized. The pilot program is a first step to obtain intellectual control of targeted properties of the nation's critical infrastructure through supervisory control policies and protocols by modeling the supervisory control policies and protocols, determining the predictive impacts related to the behavior of targeted properties, such as cascade triggers, and assessing the effectiveness of selected prescriptive measures. Here is my contact information. I would be happy to receive questions and have discussions with people on this important subject.